going to continue our discussion on epoxides, specifically their reactivity. So we already started talking about how to make them. Come on. So now we're going to talk about their reactivity, and we've already seen the reactivity a little bit, because we've looked at using epoxides to form our anti-dihydroxylation, where we have a nucleophile, and our nucleophile is our water. So we're going to look at that more closely. Typically, even though epoxides are found in nature, they're not usually what we're trying to get in our final product. We're usually using our epoxides as a intermediate compound to get to another functional group because of their reactivity and their use in synthesis. So that's really typically why we use them. It's not usually for a final product. This thing's going to come back on. So we're going to be looking at the nucleophile's ability to attack the epoxides and the different reactions we can undergo. So looking at our epoxide and its reactivity, we see we could have a possible 4R groups. Our main parts of reactivity, we have our partial negative oxygen, and we have two partial positive carbons, which can be attacked by a nucleophile. We also have two lone pairs. So those are our reactive groups, or reactive portions of our epoxide. So with those reactive portions, we're going to look at the ability of a nucleophile to attack our partial positive positions. And we're going to first just look at a symmetric epoxide, but then we're going to talk about regioselectivity. Which of the two carbons are most likely to be attacked? And that really depends on the conditions that we use, whether we use a strong nucleophile or whether we use acidic conditions. And we'll also talk about why we use acidic conditions. So really, any nucleophile can attack an epoxide. And that could be a strong nucleophile or a weaker nucleophile. But a weaker nucleophile, we're going to have to do something to make the reaction better. Now, we're only going to attack one of the carbons, and our carbon already has 4 bonds. So that means that once a nucleophile attacks one of the carbons, the ring's going to have to open. And the alcohol portion is going to be a leaving group, depending on which of the carbons it attacks. Because remember, we can't have 5 bonds to carbon. So we're going to be looking at that in a lot of detail. So here's just some examples of some different nucleophiles. Now these are all strong nucleophiles, and we're going to talk a little bit more about that. But all of these cases are strong nucleophiles, and in these cases we're forming a new nucleophile carbon bond. In this case, our nucleophile position is our lone pair and our oxygen, so it forms an oxygen-carbon bond. Here, we have the cyanide group, which is this. That's our cyanide carbon. It's a very specific compound that can attack. Not used as much the cyanide we're going to talk about in a lot of detail as an intermediate and what we can do with it once it's on there, but the problem is cyanide is super poisonous, so you got to be really careful if you're using sodium cyanide. We don't typically like to keep it in labs, so it's really dangerous. Then sulfur can be a nucleophile. We're going to look at sulfur more today as well. And then, of course, our Grignard, our carbon nucleophile, and our hydride nucleophile. That can also attack, and then we form a hydrogen-carbon bond. And in all of these cases, what we result in is an alcohol and a new nucleophile carbon bond. But notice the new bond is on a different carbon than the carbon of our alcohol. So regiochemistry and stereoselectivity are going to be looked at. And if we start with a weak nucleophile, we're going to have to protonate the alcohol first to make it a good group. And we're going to look at that in more detail as well. So let's first look at this reaction with the strong nucleophile. Mostly our strong nucleophiles are also strong bases, so we're only going to see negative charges in these mechanisms. Except for thiol. Thiol's not really as strong of base, so we'll talk about that. So when our nucleophile attacks one of the partial positive carbons, that's going to open up the ring because our carbon can't have 5 bonds. And in this case, this is a symmetric nucleophile, so we could show the attack on either of the carbons. We'll talk about regioselectivity. So that forms a new nucleophile carbon bond, and of course, this oxygen in blue was the original oxygen of the epoxide. So that thing needs to react. It's pretty reactive. It has a negative charge. So we're going to look at it being protonated at the end. Now, comparing that to our ether, we know nucleophiles don't react with ethers very well. The difference really is in the activation energy, which comes from the fact that the epoxide is not as stable as an ether is. So with the epoxide, that first step of opening up the ring, because our epoxide is so high in energy, it's going to be exothermic, and it's going to be favored spontaneously because opening up the ring relieves ring strain. Remember, a 3-membered ring is not very stable. It doesn't have those tetrahedral angles that the carbon wants. And that's your main difference in reactivity between your epoxide and your ether. Now, this isn't the same reactivity in like a 6-membered ring with an alcohol in it, because that one doesn't have ring strain. So that's why that 3-membered ring is key and why it's so useful as a synthetic strategy. Compared to an ether, this is just a whatever ether. An ether is very stable, so it starts off much lower, and it's going to be non-spontaneous to have a nucleophile attack. So that's why we don't get reactivity with ethers. We wouldn't expect that reactivity to occur. So the difference is opening up that ring was already unstable, and now when it's open, it's much more stable. Then a source of a proton is needed to protonate our oxygen that came from the epoxide to make an alcohol. In this case, we're showing the nucleophile as the OH negative, but any strong nucleophile, this is pretty much the same mechanism. The only difference is the new bond. In this case, it's between oxygen and carbon, but it would be between any nucleophile carbon of our epoxide. So let's look at this. Well, the epoxide ring opening is regioselective depending on the conditions. So under strong nucleophilic conditions, the nucleophile is going to attack the least substituted position because this is very much an SN2 type reaction. So as you can see, the nucleophile attacks and the leaving group leaves. Now just because the leaving group is still attached on another carbon of the reagent doesn't make it less of an SN2 reaction. So it's still an SN2 type reaction where the leaving group leaves as soon as the nucleophile attacks. So because of that, the less sterically hindered site is going to be the more reactive site. So we're going to get the less sterically hindered attack is going to be more likely. So what we have here is really this is a tertiary carbon, and this is a primary carbon. So of course, in an SN2 reaction, you would expect the primary carbon to be attacked easier because of sterics. Now the sterics aren't as severe as they are with a normal sp3 carbon, because remember the bond angle here is not quite 109 because the ring is making this angle smaller. So these angles are a little bit bigger than a normal sp3 carbon that's not participating in a ring. Because that ring is holding, one of the reasons of the ring strain is because we're not at that ideal 109.5 degrees, because these groups are closer together than they want to be. But when that happens, that allows these groups to be a bit further apart. So while it's still sterically hindered, it's not as sterically hindered as a normal sp3 carbon because of the ring strain that we have. Now, because it's SN2, what do you think that's going to do for the stereochemistry? Add the carbon that the attack occurs. The stereochemistry is going to be inverted, just like any SN2 reaction, at the carbon that the attack occurs. So in the second example, stereochemistry is shown. Of course, this is the more sterically hindered site, so that one's blocked, so the attack will occur here. And the attack has to occur on the backside of the epoxide ring. So if the epoxide ring is coming forward, then the nucleophile must attack from the back. It's going to attack at the least sterically hindered site. So notice that the inversion at this position is inverted. The stereochemistry at this position is inverted, just like any SN2 reaction. Also notice the stereochemistry is not affected at this carbon because the reaction didn't occur at that carbon. So the OH is still attached there, and it's still at the same stereochemistry that it was before, because that's not where the attack occurred. But just like any SN2 reaction, the stereochemistry is inverted when we're talking about using a strong base. So using a strong nucleophile, typically those nucleophiles have that negative charge. That's talking about a Grignard, that's talking about a hydride, that's talking about an alkoxide, and also thiols. Those strong nucleophiles are going to attack the least sterically hindered position and give you the inversion of the stereochemistry. If you have a weak nucleophile, the regiochemistry can be different. Also, the mechanism's a little bit different as well. So with a weak nucleophile, we don't promote that first attack as well. And under weak nucleophilic conditions, the alcohol or the oxygen isn't a very good leaving group with a negative charge. So just like in our acidity, let's look back at our mechanism. In our acidity mechanisms, we're really looking at this forward reaction. This is really reactive, so that's causing this it to be spontaneous. But this reagent has a negative charge, and this has a negative charge. So that's okay. It's an okay leaving group in these conditions. Because these are, again, hydroxide is not only a strong nucleophile, it's also a strong base. So we would expect negative charges. But if our nucleophile is neutral, then for it to attack, actually let me show that before we do that. If our nucleophile is weak, so typically our nucleophile is neutral when it's weak. Remove our R groups just for this discussion. So let's say we have something just like an alcohol. Our alcohol is a weak nucleophile. It does have a lone pair. If it attacked, we'd still open up the ring. What we end up with is an intermediate where our nucleophile has a positive charge and this oxygen left with a negative charge. And this is not very stable because we have a compound with both a positive and a negative charge in it. Remember, the more charges, the less stable the compound. So if we're using a weak nucleophile, we need to make our alcohol or our oxygen a better leaving. Because here it's leaving as negative, and since this is neutral, it's just not strong enough for this. And you'll get some reaction, maybe depending on the nucleophile, but you won't get a lot of reaction. So we can make this reaction faster by promoting it with reacting with acid first. And this is actually the reaction we did with the anti-dihydroxylation, where we first made the epoxide and then reacted it with H3O+. So in that case, what we're doing is we're protonating our oxygen first, and this is going to make that oxygen a good leaving group, because now it has a positive charge and it's going to leave neutral. So when our nucleophile attacks, in this case we're showing it with our, if we're using a halogen, but this would be true if we were doing this in our nucleophile as an alcohol, or in the case of our anti-dihydroxylation, it's water, which we've seen there, whatever it is. Then we get the attack, and our oxygen left with a neutral charge, so it's already an alcohol and it's more stable. So this just promotes the attack. This does, or can, not all the time, but it can affect our regioselectivity. So we're going to discuss that and how it affects the regioselectivity. So we are going to look at that. With the anti-dihydroxylation, it wasn't really that big of an issue because we had an oxygen on both carbons. Regioselectivity didn't matter. But if it is anything else besides H2O that is acting as a nucleophile, the regioselectivity does make a difference. So we're going to look at that. So for example, with H2O, this would give us our anti-dihydroxylation product, but we can also do this with acid. Usually, if we're doing a nucleophile like our alcohol, our acid that we're using is most likely H2SO4, or an acid that doesn't have a conjugate base as a nucleophile. So HCl, HBr is conjugate base as a nucleophile. We might get a mixture of products. So typically we'll use H2SO4. Its conjugate base is not a nucleophile, so we don't have to worry about it acting as a nucleophile. So of course we have our anti-dihydroxylation if we use H2O. If we use our alcohol, we'll get the product like I showed on the board. But of course our first step is protonating the oxygen of the epoxide to make it a good leaving group. So looking at that mechanism, and this is the same mechanism that we looked at for anti-dihydroxylation. Again, it gets protonated, and then either, if this is our alcohol, this is an R group. If it's water, this is a hydrogen, but the mechanism doesn't change because the oxygen is still the thing that's a nucleophile. Notice that it's attacking, and it's still going to have a positive charge, but the part of the oxygen that was the epoxide leaves neutral. So all we did was activate it. We made the activation energy lower because when the epoxide is protonated, it's even more unstable than the normal epoxide. So our last step, if we're starting with a neutral nucleophile, is going to be to deprotonate it at the end so it doesn't have a charge in the final product. Now, like I said, this can affect the regiochemistry and stereochemistry. So experimentally, what has been found that if we react under acidic conditions, this is specifically acidic conditions, if we react under acidic conditions, our epoxide, and we have a primary carbon of the epoxide and a secondary carbon of the epoxide, you get the product that you expect, which is the attack on the primary carbon. That makes sense. But what was actually found, which was surprising, was that if you did this under acidic conditions and you had a primary carbon and a tertiary carbon, the attack always occurred at the tertiary carbon. You will not see this in the basic conditions, but this was something that was seen in the acidic conditions. So that was a bit perplexing, but it actually makes sense if we really look at the intermediate why that might occur. So here is a case where sometimes in organic chemistry, well, oftentimes in organic chemistry, there's two things that we're considering for reactivity and where reactions can occur. And those are electronics and sterics. Sometimes electronics and sterics are in agreement. In this case, they're not in agreement. And we've seen this before when we discussed looking at the difference between SN1 and SN2. SN2, we get the attack at the least substituted carbon based mostly on the sterics. Versus SN1, we get the substitution at the most substituted carbon based on electronics. Electronics just means which is the most stable charge or the most stable electrons. Sterics has to do with space. This is the case where we have, in this case, primary versus secondary. Primary is getting the attack, and that's because of sterics. But if we have a tertiary carbon, tertiary is going to get the attack because of electronics. So they're not in agreement, and depending on what our reagent is, what our epoxide looks like, one can win out more or the other. And understanding those differences is really important. Now, sometimes electronics and sterics are in agreement, like with our BH3 reaction. We can understand why it is the anti-Markov-Makov hydration. And both sterics and electronics are in agreement. But a lot of times they're not in agreement. So we have to decide which one wins. And we decide which one wins typically by experimentation, by seeing what products we actually form. So that's the case here. So let's look at the actual intermediate, or even not even intermediate, the transition state, to look at what's happening. So first off, the base catalyzed, we're really only looking at sterics. So the base catalyzed is always going to be the attack in the least substituted position, no matter if we have tertiary, secondary, or primary. When we're comparing, we're always comparing against two positions for the epoxide, so the least substituted is always going to be the case. But with the acidic conditions, something's different. And the thing that's different with the acidic conditions is if we look at the actual intermediate. So let's look at what's going on. And then the other question is this more like SN1 or SN2? If the nucleophile is attacking the tertiary carbon predominantly, then this is more like an SN1 reaction. But we don't actually expect a full SN1 reaction. If the nucleophile is attacking the least hindered site, that's more like SN2. So what's really going on? And what's really going on, the other thing that really kind of brings you to it is, let's say we have the attack occurring here. What is seen is we still get the inversion of stereochemistry. Here our attack is our OR group. So that's our nucleophile, it's neutral. And notice that where the attack occurred, we did get inversion of stereochemistry, where we had to attack from the back side. That pushes the methyl forward. And now our OR is opposite from where our epoxide was. So that suggests that even though it's attacking in the tertiary position, it's still going through an SN2 type of reaction. Because remember, SN1, if it formed a full carbocation, would only give us, would give us both stereochemistries. And we don't see that. So what's actually going on, and what's actually going on is this, looking at our transition state. It's very similar to our bromonium ion, because they all look very similar. That we really have a resonance structure between the oxygen having the positive charge or the carbocation actually being there. And in that resonance structure, means that we're gonna have a very strong partial positive at the carbon that's attached to our epoxide. And what that happens is that the carbon that's more substituted is going to have the more stable partial positive charge. So when we looked at our reaction with our bromonium ion, and when we did it in the presence of water as a solvent, we always said that the water, once the bromonium ion was formed, was going to attack in the most substituted position, and it was because the positive charge, that partial positive charge was more stable, because we have that resonance structure here. And our other possible resonance structure would have the positive charge here, but that's not as contributing because that positive charge isn't as stable. So when we have a tertiary carbon with an epoxide present, it's the same concept. But we only really see that winning out when it's tertiary. When we don't have a tertiary carbon, we don't see the electronics winning out. So this is the case where the electronics means that the partial positive of our propated epoxide for the carbon that's more substituted is more stable. So electronically, that position is going to be more susceptible to attack. So in summary, the regiochemistry outcome is dependent on what the epoxide looks like. If we have no tertiary carbon, then the attack's going to happen in the least substituted position because this isn't stabilizing the electronics that much better because it's secondary versus primary. But as soon as we have a tertiary present, that's going to stabilize the positive charge better, and then electronics is going to win over sterics. And again, typically we can have an SN2 reaction at a tertiary position, but this is still sterically hindered, but not as sterically hindered as a normal tertiary carbon because the bond angles are bigger because of this ring. So you can actually have it. So if you have a tertiary carbon, the attack's occurring there. If you don't have a tertiary carbon, the attack's occurring in the least substituted position, because then sterics wins. So it's all about what wins, what's going to be more stable in the transition state. And you really can't predict that until you look at it experimentally, but those experiments have been done, so now you can predict it based on other people's experiments and what has been reported. Now, this is only relevant in acidic catalyzed conditions. Under the basic conditions, we do not have one of the partial positive charges being more stable than the other, so it's always going to be sterics. So it's only under acidic conditions that this is appropriate or even something that we care about. So if we look at this example, and we're trying to figure out the best conditions, first off, the thing to consider is what's our nucleophile? Well, we end up with a diol, so our nucleophile must be either water or OH minus, because that's our new bond. And it's hard to really tell just from looking at this which of these oxygens were originally from my epoxide. And the only reason why I can look at it and know which of those two oxygens was originally from my epoxide is the chirality. If chirality wasn't shown, I wouldn't know which of the two was from my original epoxide. But I do know which of the oxygens is from my original epoxide. And it's oxygen 2. How do I know that that's the oxygen that was originally from my epoxide? Say that louder. That oxygen did not change stereochemistry. That carbon has the same stereochemistry. So remember, you're going to have the backside attack, whether it's acidic conditions or basic conditions. It's still an SN2, mainly SN2-like reaction. So therefore, if your stereochemistry is not inverted, then the attack did not occur at that carbon. So I know that that oxygen was the original one because the stereochemistry is the same on that carbon. So I know that oxygen 1 is my nucleophile because this stereochemistry was inverted. This CH3 group was pointed back, now it's pointed forward, and my OH is on the opposite side. If the reaction didn't occur at that carbon, the stereochemistry can't be inverted. We cannot invert stereochemistry without a reaction occurring. So that tells me which of the two oxygens was originally in my epoxide. So that means my nucleophile attacked the tertiary position. So we have a primary position versus a tertiary. If we want the attack to occur in the tertiary position, we have to use acidic conditions. Because under basic conditions, it's never going to attack the tertiary position. It's always going to attack the most substituted. So in this case, I know my nucleophile is OH. And under acidic conditions, my nucleophile is going to have to be H2O with acid present. So you can write that as H plus and H2O, or you can just write that as H3O plus. Either way is acceptable. But what we see is if we're forcing the attack in the tertiary position, we have to use acidic conditions. There is no way, really, at this point from what you know, to force the secondary position over primary. But we can force a tertiary attack. If there's no tertiary carbon, then the least substituted is always going to be attacked. So that's what we're looking at. So looking at this one, what we have here is a primary I wrote that wrong. This is secondary. There's only one hydrogen. What we have is a primary versus this has one hydrogen, so a secondary carbon. It has one R group and two R groups connected to C1. So it doesn't matter whether we use acidic or basic conditions. We don't have a tertiary carbon, so therefore we're only ever going to get the least substituted position. So that means none of these would work. So the difference in conditions only makes a difference with regioselectivity if you're trying to get the tertiary carbon to be attacked. And remember, under strong nucleophilic, or as we say, basic conditions, then we're always going to get the attack in the least substituted position. So now we're going to talk a bit about how our epoxide can be used for synthesis, which is really how it's usually used. So epoxides can be used to install functional groups adjacent carbons or alcohol. So let's look at this example. Here we want a cyanide, a CN, bond, and an OH. Well, we can go through an epoxide. Our first route would be to make the epoxide with MCPBA or just using our peroxy acid, whichever. Followed by, and cyanide's always a strong nucleophile. You can't make cyanide a weak nucleophile. Cyanide is a strong nucleophile. It's C triple bond N with a negative charge. So followed by cyanide. Now cyanide's pretty reactive, so you have to add water second, because otherwise it'll just react with water. Of course, we're going to attack the least substituted position because these are strong nucleophilic conditions. So that's a great route to give us a new cyanide bond. We also have an alcohol there. Now, typically though, the epoxide is used as a new route to a carbon-carbon bond with our Grignard reagent. So our Grignard can be a nucleophile. I mean, not just can be, our Grignard is a very strong nucleophile. And just like when we reacted our Grignard with a carbon-oxygen double bond, we have the same considerations. We can't have an acidic proton present. Water can't be present. But once we make our Grignard reagent, it's a strong nucleophile. It's going to attack the least substituted position. We open up the ring. Water will protonate our oxygen. Now, there is a difference between using the epoxide with the Grignard and the carbonyl-carbon with the Grignard. And the difference is subtle, but it does make a difference. So typically, we can take an alkyl halide, react it with magnesium, then we can react it with an epoxide of our choice, and what we form is a new carbon-carbon bond and an alcohol. So that's true of both the carbonyl and the epoxide, but the difference is where the new carbon-carbon bond and the alcohol bond is. So with the carbonyl, the scomono, the Grignard attacks the alpha carbon right here. That means that the new carbon-carbon bond and the alcohol is on the same carbon. The difference between that and the epoxide is that the epoxide attacks one of the carbon, the Grignard attacks one of the carbon of the epoxides, and then the ring opens. So that means the new carbon-carbon bond is on carbon 1 and the alcohol is on carbon 2. Versus the carbon-oxygen double bond, the new carbon-carbon bond's on 1 and the alcohol bond's on 1. So the difference is subtle, but it makes a huge difference in your final product, in your connectivity. And remember, connectivity can affect reactivity, it can affect physical properties, and if you're talking about for drug synthesis, it can be the difference between killing your patient and your patient being treated. So it makes a difference where this new bond is. And you have to pay attention to that in synthesis. So the position is different. So this is just the summary. Carbon-oxygen double bond, we attack the alpha carbon here. So the alcohol and the R group is on the same. But with our epoxide, we attack one of the carbons that opens up the ring, so they're on adjacent. So when we're looking at a synthesis, here's the first example. Let's look for our new carbon-carbon bond. We're starting with an alkyl halide. Here's our original 6 carbons. Here's the new carbons, and our new carbon-carbon bond is between 2 and 7. Notice where my alcohol is versus where my new carbon-carbon bond is. My alcohol is not on the same carbon, it's on the adjacent carbon. So that means that we're going through an epoxide. The epoxide that we're going through would be the epoxide where we have a bond between our oxygen on 8 and 7. So there we go. This is 7 and 8. And of course we get the attack on carbon 7, which is what we expect. Now conversely, We're starting with the same starting material, and we're adding the same number of carbons in this example, but notice the difference of where the alcohol is. Here, the alcohol is on the same carbon as our new carbon-carbon bond. So in this case, we're going through the carbon-oxygen double bond. We're still adding 7, 8, 9, 10, and 11, but what we're starting with is different. It's a slight difference, but it is a difference, so we have to pay attention to it. And looking at this example, if we're looking at this example, we're only given epoxides in this case. So in this case, here's our new bond. Notice that our alcohol is on the second carbon. So we're going to take our alkyl halide, react it with A, and then we're going to react it with H. That leaves our alcohol on carbon 2. Then if we want to oxidize it, we can, and we can oxidize it with our chromic acid or PCC because it's a secondary alcohol, so it doesn't matter. Because we're going to get the same thing. So before you leave today, I'm going to introduce you to sulfides and thiols, and we're going to finish up this chapter really quickly on Monday. There's not a lot we're going to be talking about sulfides, sulfur, and thiols. I just want to talk about naming today. So sulfur appears under oxygen on the periodic table. We call them thiols, SH groups, and they react very well. Oxygen, when it has one bond, typically has a bond with hydrogen, so one carbon bond, so we have alcohols. When sulfur has one carbon bond, it typically forms a thiol, an SH. The name is very similar to how we name alcohols if we're naming it as our parent. So we have butanol here. If this was a thiol instead, it would be butane thiol. Now we do keep the whole ane because this is the differences between a vowel and consonant with the T. So it's not butathiol, it's butane thiol. But overall, the naming system is the same if it's part of the parent. The difference really with naming comes from if your thiol is a substituent. If your thiol is a substituent, usually because you have a more, what we call priority functional group, then your thiol is called a mercaptan. So for this case, alcohol takes priority over thiol. So our parent is named for the butanol. So therefore, our thiol is a substituent. So when thiol is a substituent, it's called a mercaptan. That comes from the fact that thiols complex mercury really strongly. So that's where the merc comes from. So it's named based on their ability to complex mercury. In fact, if you were to get mercury poisoning and you went to the hospital, they'd give you this compound, dimercaptopro, which is really 2,3-dimercapto-1-propanol, because it would bond really, really strongly. Now, it still might not help you. You still might die if you don't get to it fast enough, but thiols are used to clean up mercury. They also smell really bad. Skunks have thiols when you have a skunky skunk. And also, when you smell natural gas, you're not smelling natural gas. You're actually smelling methane thiol that's added to natural gas, so we can actually smell it. So we're going to talk about the properties of thiols on Monday and really finish this chapter because it's not very long. We won't talk about thiols for too long. Have a good weekend.